Okay, welcome to Chapter 7, Part 2. We are going to get into substitution, but very specifically in this part, we are going to be talking about the SN2 mechanism. And so let's get in. So we know that very generally, we are going to be taking an alkyl halide substrate. We are going to be taking a reagent, and since it is a substitution, our reagent is going to be a nucleophile, and we are going to be replacing the halogen with the nucleophile. So, of course, we'll also have some halide over here. Oftentimes, our nucleophile has a charge as well. Now, there are two possible mechanisms. There is a concerted mechanism, and that is the SN2, and that is what we're going to be seeing in this part. And then there is stepwise. So concerted versus stepwise is one of our first topics. A concerted mechanism is going to show all of the bonds breaking and forming at one time. So in this case, the concerted mechanism has the nucleophilic attack and loss of leaving group happening at one time. A stepwise mechanism is going to have those same two steps, but happening one at a time, right? The leaving group leaves first, and then the nucleophilic attack happens. And it may be crossing your mind, well, why do we care? We get the same product at the end. Well, that's exactly what this whole class is about. We care about how a reaction is occurring, what bonds are breaking and forming, and in what order, or is it happening at the same time? It's important because it helps us to understand why certain substrates react or don't react, why certain products form or don't form. Helps us to identify if multiple products are made, which one are we going to get the most of? What is the major product? And so this whole class is going to be about this story of bonds breaking and forming, and concerted versus stepwise is important. And this, how do we know that these things happen? Well, it all comes down to experimental data, kinetics information, and we will talk a little bit about that as we learn about the SN2 mechanism. So we are going to concentrate on the concerted mechanism first. In a future part, we will get into the stepwise SN1 reaction. So very general mechanism. Now, this is a very important vocabulary word. When I ask for a mechanism, I am not asking for starting materials yield products. I am looking for the curved arrow notation, the story of how we go from starting material to products. And so the mechanism of the SN2 reaction, you are going to have an area of electron density. There will be some sort of lone pair most of the time in your nucleophile that will be attracted to the carbon in the substrate that is attached to the halogen. Because remember, that is going to be a big old partial positive carbon. It's a good electrophile. So you're going to get an arrow from your nucleophile to that electrophilic carbon. We can't have 5 bonds on carbon, and so we are going to get that loss of leaving group at the same time in one concerted step, right? And that will leave us now with a new bond between the carbon and whatever the nucleophile is and our halide ion. Now, what does SN2 mean? So the S is substitution, of course. The N is nucleophilic, right? We have a nucleophile coming in and doing the substitution. And then the 2 is a kinetics indicator. This is a bimolecular reaction or bimolecular rates determining step. If you remember from kinetics, it means it's going to be second order. We will, let's see, how would you design an experiment to confirm this rate law? So what this really comes down to, and it's probably on another slide, but it's what we're going to talk about right now. So the bimolecular. What I want you to notice is both of these starting materials, the nucleophile and the substrate, they are both involved in the rate determining step. There's only one step, right? So you have two molecules involved. Now, if you were going to set up a kinetics experiment to prove this, you would hold one of them constant and change the concentration of the other and then track the rates. In a bimolecular reaction, changing the amount of nucleophile will affect the rate. Changing the amount of substrate will affect the rate, right? So if you double the nucleophile, the rate should double. If you double the substrate, the rate should double. They are both important to the rate. That is how this gets determined. And so we're going to see that in comparison to a unimolecular mechanism. That'll be 2 or 3 videos away from this one. Okay, so here's a specific example. And there are going to be several things we need to think about with the SN2 mechanism. We are going to talk about the substrate, what makes a good substrate, and within that we're going to talk about stereochemistry. We are going to talk about the reagent, what makes a good nucleophile. We're going to talk about solvent. These are all going to be important points. It's very important to stay organized in Chapter 7 because we have 4 mechanisms that we're going to discuss: SN2, SN1, E2, and E1. And there are going to be issues with the substrate, the reagent, and solvent for all of them. So we want to stay very organized. So the first topic we are going to tackle here with the substrate is stereochemistry. Something to note, Breeze is saying hello. Something to note in the SN2 mechanism is that you get an inversion of stereochemistry. Now this, and I'm just going to put stereochem. There we go. This is relevant when the carbon that is being attacked is a chiral center. If it's not a chiral center, it doesn't really, there's not an effect on the product. But when there is a chiral center, it's really important. So what I want you to notice is we have an S chiral center here, right? The bromine, the ethyl, methyl, hydrogen's coming towards you. If you connect this and take in your, your rules for configuration, this is an S. Notice that the nucleophile here is an SH ion, and the S is on the opposite side. The S is also priority 1, just like the bromine was, 2, 3, and 4. But now we've had an inversion of configuration. S becomes R. This has everything to do with the mechanism, which is one of the reasons why mechanisms are so important. It helps us to predict that stereochemistry in our product, right? So let's think about how that works. Let's think about that mechanism. The SN2 reaction is referred to as a backside attack. So let's think about that example on that last problem. If we have a carbon, and that bromine is here, and we have whatever was attached. Let's see, we have methyl and ethyl, and so one of them has a carbon like that. If our nucleophile, this little S ion here, is approaching, think about where is going to be the easiest place to approach, because we know negative is attracted to positive, but negative is also repelled by negative. So this cannot approach from the side where the bromine is. The bromine has a lot of electron density, right? The back side, so you're seeing that here, right? There's a lot of electron density over here. Whereas the back side, the other side from where the leaving group is, that's going to be where that partial positive is strongest, right? You're not going to have a lot of electrons there repelling. And so that sulfur is going to approach from the back if where the bromine is considered the front. All right, so it's going to approach from a specific kind of 3D geometric position. It can't just attack that carbon anywhere. It's got to come in from the opposite side of the bromine. So, and we're going to see a picture of a transition state here. Let's blow this up a little bit. Okay. Let's talk about this. When you see the brackets and the transition state symbol, this is showing you between steps. This is showing you this high energy moment when a bond is breaking and a bond is forming. So in this case, I'm going to, I want to erase this here. I'm going to come down. I just want a little bit more room. The sulfur-carbon bond is forming. The carbon-bromine bond is breaking. Now, you cannot isolate transition states. This is not an intermediate. It is a transition state. It is going to be the highest point in the energy diagram. What is going to happen to the other bonds? So I'm going to go based off my drawing. The hydrogen was still in the plane. That methyl group is still going to be coming towards us, but is starting to shift back. And the ethyl group also starting to shift as the bromine is leaving, starting to migrate to that side. So we get this flip, right, in our stereochemistry. The sulfur adds to the opposite side. You could certainly draw it based on how this is drawn on this slide as well. I don't know. If we blow it up, we can draw it here. The sulfur, again, adding to the side, opposite where the bromine is leaving. Here, the hydrogen was going back, so it's just starting to shift more to the right. The methyl's still going to be going to the front, but shift more to the right. And same with the ethyl. It's still in the plane, but it's going to shift. All right, it's just showing you the bonds breaking and forming in those transition states. Now, in most mechanisms, we don't draw all the transition states because it would be a lot, and it is what is implied by the arrows. But it is helpful to do this in our first mechanism to really start to understand this inversion of stereochemistry. I've seen in some books it being referred to kind of like an umbrella flipping out, right? Anything coming towards you, still coming towards you. It's just kind of pointing in the other direction. The SN2 prediction. So we're still talking about the substrate, but what is going to make a good substrate for SN2? For an SN2 reaction, sterics are important. And so the less hindered the backside is for attack, the better. It is going to be much easier. So this is going to be the fastest, most reactive substrate in an SN2 reaction. It's going to be a methyl halide because the hydrogens are small. They're not providing any electron density, right? They're just like little exposed protons. Then a primary alkyl halide will be the next fastest, and then secondary, right? So that's the fastest. This is going to be the slowest. I left out tertiary because tertiary substrates do not undergo SN2 mechanisms. Highlight this, put neon signs around it. Record this in a small recording and play it to yourself while you're sleeping. Tertiary alkyl halides do not undergo SN2 reactions. When you come to a problem and you have to decide what mechanism is this substrate and reagent going to go through, if you recognize a tertiary alkyl halide, you can take SN2 off the table immediately. So please make sure that you understand this. We will come up to this several times throughout our discussions in Chapter 7. And it's because you're blocking this little electrophilic carbon. There's just R groups all around it. And so your reagent, your nucleophile, can't get to it, right? It's sort of like all of these groups are protecting it. And so your nucleophile is like, how do I get in here? I can't. It's blocked. So the methyl group will go the fastest because there's nothing blocking it. Primary goes relatively fast as well. Secondary is slower, and so there's some interesting discussions to be had around secondary, but it can happen. And then tertiary will not happen at all. And this was discovered through experimental observation and studying reaction rates, right? If we kind of have a baseline of our primary alkyl halide in a SN2 reaction, and we say that rate is 1, the methyl halide is much faster, the secondary halide is much slower, and then the tertiary halide doesn't really happen at all. It has to do with reaction rates often have to do with the energy of the transition state, right? And that activation energy is just higher when there are bigger groups sort of getting in the way. It makes those bonds breaking and forming, particularly the bond forming, it makes that harder to happen, right? It makes it, there's more electron density repelling that nucleophile. And so when you're comparing methyl, primary, secondary, it's just going to be larger activation energies. Okay, we're going to keep going through there. Now, okay, so for our substrate, right, we know there's going to be inversion of stereochemistry when we have SN2. And we know sterics are going to affect rate, or if the reaction can happen at all, right? And that's primary, secondary versus tertiary. So then what about the reagent? For an SN2, we need a strong nucleophile. We're going to be talking about nucleophiles and bases, but also strong versus weak. A strong nucleophile is required for SN2 reactions. And the main thing to note is, let's see, we're gonna have a table later on where you will want to memorize, and I will put that up on eCampus for you as well, of what categories or what falls into what categories. Strong nucleophile, strong base. Weak nucleophile, weak base. So let's talk about what is strong versus what is weak. A strong nucleophile often will have a charge. It could be an OH, could be an OR with a minus, could be the sulfur derivatives. There are a bunch of different options. It could be a different halide ion. Could be a nitrile. There are a few others as well, But the main thing that I think is helpful is this category is much, much smaller. A weak nucleophile is water or an alcohol. Everything else falls into some sort of strong category, right? So the only thing that always comes out as weak is water and an alcohol. So if it's something else, it's either going to be a strong nucleophile or strong base or both. And so all of these are strong nucleophiles. You even get H2S as a strong nucleophile. Thiols are strong nucleophiles. So they're not always charged. But weak is going to be water and alcohol. Oh, let's see. Did I miss anything? We have our halides. We have our S ions, our O ions, and our cyanide ion. And then your weak nucleophiles are water and alcohol. You need to commit this to your memory because you're going to have to look at a reaction and decide, is that reagent strong or weak? So you want to start committing these things to memory. In general, your anions are going to be strong, right? It's got so much electron density, it has a formal charge. Polarizable atoms are also good nucleophiles. That's why you might see the neutral sulfur atoms working as nucleophiles. They're larger than oxygen. They're more polarizable. Solvent will also affect nucleophilicity. And so since there is not a slide before we go to part 3, we're going to talk about the solvent as well. So for solvent systems, there's 2 different types of solvent. There is protic versus polar aprotic. Okay, so what is the difference? A protic solvent, something with a hydrogen that can hydrogen bond. A polar aprotic solvent cannot hydrogen bond. Oh, goodness, excuse me. Okay, so big difference. Your protic solvents are going to be water and alcohols. I know that also can be your weak nucleophile, but oftentimes when we look at a reaction and we have a reagent on top, we will sometimes see a solvent on the bottom. Okay, water can be a reagent or a solvent, same with an alcohol. A polar aprotic solvent, there's several out there, but I want you to know 3. I want you to know DMSO, DMF, and acetone. So I want you to know those 3 particular types. All right, so let's see, we'll go like this. Acetone, here you go. It is polar. You have that polar carbonyl, but there is no hydrogen on the oxygen. DMSO is dimethyl sulfoxide. Let me draw that out for you here. Let me see. Dimethyl sulfoxide. That's right. Sorry. I just wanted to double check. It looks like acetone, except it has a sulfur connected to the oxygen instead of the carbon. And then DMF is dimethyl formamide. And so it is a carbonyl attached to an amine. Now, you don't need to know the structures, but you need to know these 3 acronyms or names. DMSO, DMF, and acetone. Why is this important? polar aprotic solvents are better for SN2 reactions. Why? Let's think about what's happening here. For an SN2 reaction, you need a nucleophile to be able to get to this carbon here, right? So we already know that what these groups are can hinder that or can help it by either being small like hydrogen, or it can hurt it by being large R groups and blocking it. But what happens when you have a nucleophile and you have a protic solvent? If you have a protic solvent like water, you are going to be getting a lot of strong intermolecular interactions. And that is, you're going to have all that water, right, forming all those interactions or alcohols and really surrounding that nucleophile, right? And this is going to be a steric issue with the solvation, right? It's going to really solvate it. It is going to stabilize that nucleophile. It won't be as reactive, and it'll block the SN2 reaction from occurring, or it'll slow it down at the very least. Whereas a polar aprotic solvent, right, and we're going to reiterate here, good for SN2, is not going to solvate as well. It's still polar, so it can still dissolve, but you're not going to have those strong sort of hydrogen bonding type interactions. And so the nucleophile is more free, right? It's more free to attack. It's not as stabilized, so it is more reactive as well. So to recap before we move to elimination, things that you need to know about SN2 is inversion of stereochemistry. So when you predict your products, if you had a chiral center to begin with, and it was R, it will become S. S will become R. You want a less hindered substrate, right? Substrate, okay. Tertiary will not react. You need a strong nucleophile, not weak, so not water and alcohol. And a polar aprotic solvent is best. It's not always required, but it's best and may help us make decisions later. Now, in part 3, we will tackle our first elimination mechanism. And so, see you there.